Okay, let's start with the first and begin and finish with the 5. Yes. And it is easy to understand that L1 plus 1 component, it is 2 L1. Yes? And what it is, f from functional from here corresponds the pair y is a sequence from L1, and alpha is some complex number which is more convenient to redefine as y0. And functional acts on x as sum xk yk plus x0 alpha. And you're changing the notations as y alpha is, then you write it in the same way as an C0. Yes, the same way as C0. If you redefine, so it is L1 with one additional component. And the norm of this functional is the norm of y in L1 plus this, so it is the norm of this sequence AK, but from 0 in L1. So it is easy to understand why it is in this way, because C, the space of converging sequences, distinguished from C0 only one dimension. Only one dimension. So let's take x from from C. It have a limit. Let's define it as n. Take A0, 1, 1, 1, 1, and write this element. From what space this element? From C0. From C0. From C0, because we subtract the limit.
I thought you asked about the...
Yes. So by previous theorem, we immediately know that f on this element exists y from L1, and it is y1, y2, and so on. So that this functional looks like this on C0. Yes. Because we know the description of functionals on C0. It is isometrically isomorphic to the L1. And the norm of this functional is just the norm of y in L1. And then we can rewrite it as in what way? And it is we want to obtain linear functional on all space C. So it is equal to this, and in another this is, so it is the same. Yes? So we obtain that f of x equals the sum xk yk plus a f of a0 minus the sum so you can to obtain this, because what would take us x0? We want this, we want to obtain this formula, but we obtain this formula. This we see that this we have, yes? And it is sufficiently only to compare this writing with this writing. So take or define x0 just x0, a, it is a limit. It is a limit of this. And alpha I take as this object. And is it clear that this sum is converged, this series is converged? Because sequence y is from L1. So the sum is finite. So we obtain this description. Yeah. And is it clear that we have this equality for norm? Let's check it. F of x. We obtain this description, yeah, because by this definition. So it is this sum So if this inequality is clear, I put the absolute values inside the sum and take away from the sum the supremum of xk, just the norm of x in C, in space C. And if x0 is, this is the norm of x and C1. What you can say about the limit? X0 is a limit of this sequence. Can it be larger than the norm of element x? X0 is a limit of xk. And this is, the norm is supremum. So it is, of course, less than norm of x. So we obtain the such estimation. It means that the normal function f less than this. Question? Yeah.
How do you know that x is finite? Like x0 has a value, yes, okay. But when n goes to infinity, why does xn has a certain finite limit?
It's by definition of space C. Space C small is the space of all converging sequences.
Okay, okay.
It's by definition. This exists by definition of space C. The definition of C. They have a limit. Any element has a limit. And of course, this limit is less than or equal, maybe, for supremum of all xk's. So we change it by inequality by the norm and put this and this out the brackets. And so this sum is the estimation of the norm. And now we must show that we can obtain this number, not just obtain, but we can go nearer and nearer to this number. What we take? Take some such element. For example, we take xn equals signum y1, signum y2, signum yn, x0, x0, x0. Because x0 is the limit of this element, of this sequence. And then act by functional f on xn. We immediately obtain the sum yk, k from 1 to n. And then this is not good, I think, example. because we need to use the sums plus this sum, yeah? We need to obtain the model of alpha, yeah? We must obtain the absolute value of alpha. If I take signum of alpha, x0 is maybe we take not x0 but signum alpha and signum and so on. Then we obtain what? We obtain this, yeah? This part on multiplication on yk, yes? This from this. It's divided on two sums. And this is changed, the limit of this sequence is signum alpha, and multiplied on alpha, it's just absolute value. And then for any we have this estimation. Of course, the norm of xn less than 1, because signums, the signs. And then it is tends to the norm of y in L1. This is tends to the 0, because this is a tail of the converging sum, yes? This is by Cauchy criteria goes to the 0. And this is goes not to nothing, it is just. So for any we have estimation, for this sequence we have the limit of this. So we show that the norm equals to this number. Yes? It is about the first. So what about second? Is it clear how to solve? Just don't use this theorem. So P equals to 3. First step, you must calculate Q. What you can say about Q? Three or two, yeah. You're right. But 1 over Q is 1/3. So Q is 1 over P is 1/3. So 1 over Q is 2 over 3rd. So Q is 3 over 3 on 2. Yeah. So and we know that the norm of this functional is just by theorem of isomorphism, you can just directly write the answer. And if I choose the parameters in good way, so I obtain that it is, yes? And we calculate this series. It is, that's the answer, so that's all. Okay? Third problem. What we have the third problem? It is good example how to prove the final result. Because in a lot of problems for calculating of norms, it is easy to obtain the estimation above. But to show that it is can be realized is sometimes demand a good work, technical work. We have a functional. Let's say consider another problem. It is not interesting because more interesting take away the absolute value inside. It does change the answer because first step of estimation, you take the models, then you change the sum of absolute values, and then you put the absolute value inside the integral. Yes. So if later we can discuss the original formulation, but it is more interesting without absolute value inside. If this step is clear, there are 3 steps in one. I put the absolute value of the whole sum change on the sum of absolute values, and then I put the absolute value of integral as an integral of absolute value. Any step gives us an inequality. Yeah? Good. So this is what is a good idea in the space of continuous functions? This is values at a concrete point. Yes? At some point x, it's 1/2, it's 1/4. But the norm in space of continuous function is a maximum. Of course, maximum is less or equal to value in any concrete point. So you can write these estimations. Yes? Less than. So it is less than, let's calculate this integral of, it is 2 triangles. Yes, I don't calculate integral, I find the square of the triangles. It is the same. It's 1/2, is this 1/2, yes? So it is 1 in sum. So 1 plus 2 plus 1. So you can understand that the good estimation is 4 for this norm. And for the first problem, for this, you immediately obtain the same. Immediately obtain the same because this, if you consider the absolute value of x here, you immediately have this estimation. So this estimation is correct for the original formulation of the homework. And just now analyze this formula, and try to understand on what element you obtain this for. On this subinterval x is negative, yes? And we here obtain the absolute value of x. So, and f is norm, and we consider f which have norm 1, yes? So what change x to the absolute value of x? It's signum of x, yes? So it is -1 here. And again, on this subinterval from 0 to 1, the x is positive and f is 1, so it is this point. This is on this function we obtain just 1 for this integral, precisely 1 for this integral. This factor, not factor, the term. So that, but we have here plus, yes? Plus. And we change it on the positive number 1. So in point minus 1/2, minus, our function must be 1. Yes? And here was minus. And we put again the absolute value. So our function must be minus 1 in this point. What is the problem with this function?
It's not continuous.
Yes, it is not continuous, but it is by one move of the hand, you can change it to the continuous approximation. Take a little neighbor of the points of discontinuity. And each a neighborhood about 1 over n. It is not necessary to write a precise formula for this function. You must only understand that such function exists. These functions fn, it is continuous, the norm 1, and the f of fn, of course, go to the 4. Because we know it is pointwise converged to the function, and it's bounded by, for example, Lebesgue theorem. We have Majorand convergence. We can take the limit inside the integral, consider this Riemann integral as Lebesgue, and as a limit function we have value 4. Is it clear? Okay. The second following. ABC. I consider on seminar from CAB to CAB, yes? Yes? We consider from CAB to CAB this the integral operator. Minus 1, 1.
So just a second. Why is f of 1 quarter? Why is it? Why did we make it minus 1?
This function fn goes to the function f on which we obtain this value just.
Okay. So in order.
So we have here we have the estimations for arbitrary function, and here we present the sequence of continuous functions for which we go to the 4. And norm of this function fn equals to 1. We work on a unit sphere.
Okay.
And
Why calculated? For
why what?
minus. Okay.
Why what?
I see it
You
now.
see? Okay, good, good. So A from L1 AB to L1 AB, B from L1 AB to C AB, and here the assumption that this function is from class of continuous function on the square, yeah, of 2 variables. And ABC from L2 AB, more important situation, it is so-called operators, Hilbert-Schmidt operator. Of integral operator from L2 to with this assumption on kernel. It is function from L2 of 2 variables. So kernel is from L2, it's just the class of operators of Hilbert-Schmidt. And this is from mathematical physics, the array is green function for differential operators. For green function for differential equation. And later we make some discussion on the so-called notion as a reproducing kernel in Hilbert space. reproducing kernel Hilbert spaces is an important class of spaces. It's just interesting situation when two different theories arising simultaneously, but reproducing kernel just the same the green function. But in geometry of Hilbert space, it's arised as reproducing kernel. In mathematical physics, it's arised as green functions. But we know that in mathematical physics, it gives us the solution of differential equation. And in machine learning, it's using us to construct neural networks with learning on reproducing kernels. Later, we discuss some examples. For example, Sobolev space is Sobolev space with the reproducing kernel. And L2, it is not Hilbert space. It is Hilbert space, but it has no reproducing kernel. But it is some spoilers. So first, let's start. So it's solution of item A. It is equals to use the norm in this space L1, yes? Then again, first step is simple. Put the absolute values inside the integral. This function is continuous, so this is integrable. This is integrable. And we must do with this dual integral something to obtain the norm of function f in L1. So what we can do? We can make a Fubini theorem first. We can do it because all integrable. So we change it. This is some function on t. Yes, this is some function of t, and we must take it away from the integral. The unique way to do it with not rough estimation, maximum on t and then we just obtain only this is norm f of L1. These steps clear, yeah? So this is a candidate on norm. For shortly, I define this as M capital, and we show that the norm of operator A from L1 to L1 not less than M, yes? And now, again, we must analyze on what function we can obtain this formula. What we know about function k capital. It is continuous function. Integral on one variable is continuous function too. It is continuous function up to variable t. So what we can say? There exists point, for example, t0, such that in which we realize this maximum. Oh, sorry, here integral dx yes, there exists such point. Let's consider the following. I again show a picture. Draw a picture. For simplicity, let's consider T0 is an interior point. Is it is A or B? Then we consider two sides, one side neighborhood of end. But for interior point, we can consider two side neighborhood. this is t0 minus 1 over to n. Here t0 plus 1 over to n. And on this neighborhood, we take function equals to n. And outside this, we take 0. This is a picture, this is a graph of function fn. So on the interval with length 1 over n, we take the step of high n. So the norm of this function in L1 equals to 1. It is so-called delta sequences. Yeah, yes. We must consider some introduction to distributions or generalized function. Who hear about generalized functions? You hear? You hear? Or you? Distribution or generalized functions. So we have a short distribution, so short introduction to it. So it's in theory of generalized functions, so-called delta sequences. It tends to the delta function, and delta function is not a function; it is linear functional on local convex space. On local convex space, we just study linear functionals in norm space. But for many applications, just for physics, it's important to consider not only norm space, but convex. It's so-called polynorm space. Not one norm, a set of semi-norms, countable or not countable set of semi-norms. And physical interpretations of delta functions is observer. It's a model of observer in the point. It's observer in the point delta function. So calculate what we obtain if we use our operator to this sequence of function. So the interior integral will be only on the neighborhood. And this is just a norm. Yes? What we can say about this? See, please, this multiplication n, you can rewrite as 1 over n on the neighborhood of x0. We integrate continuous function on the small interval and divide on the length of this interval. It is middle meaning theorem. Middle meaning theorem says us for continuous function that this interior integral just equals to value of function k in some interior point. It is equal to model the absolute value that preserves. And this is k Tn dx, where point Tn is some point inside this interval. Yes? And then allow n to go to the infinity. N go to infinity, so as n tends to infinity, then Tn go to T0, yes? So this integral converge to the, and we know that in this point it is just a maximum. So these estimations is good estimations. It's just equality. So compare the difference with the problem we discussed on the previous seminar. We consider this operator from CAB to CAB. And there was integration on the second variable and maximum of the first variable. It was integration on t and maximum on x. And here we have integration on x and maximum on t. They changed. Because CAB you can consider as L infinity. L infinity and L1 are dual spaces. So the variables change with its roles. Okay, is it clear? So, and the C is from L1 to CAB, just the same, very. Because we have another final space, so we change the norm in the final space. Not integral, but maximum. Then again, put the absolute value inside integral. And now you must do something with this integral to obtain the norm of function f in L1. So we need to obtain the integral of absolute value of function f. Here we have the maximum on x depends only k. So you can write this estimation. You can take away outside the integral maximum, not only on x, but only on t, and on t2 maximum. And then you obtain the just this, and this is just the norm of function f and L1. So who is candidate on norm of operator? This guy is candidate. And again, just I take away from the blackboard. But we can say that there exists x0, t0 such that the value at these points coincide with this maximum. Yes? Continuous function on compact tends its maximum. The square is compact. So there exists a point in which we obtain our maximum. Then you must understand that maximum on x is just by the definition of the norm in the space. So, and maximum on t, you can obtain choosing the same example. So the same example gives us the answer. Because if you take this sequence, you obtain the value in this, for this variable t. And then you write the formula for norm in CAB, you take maximum on x, and this maximum on x gives us the choosing of x0. So this example gives us the answer. So the norm equals for this. Is it clear? And the last was what problem? From L2 to L2, yes? The C. But there was more easiest formulation because the task was only obtain the estimation. So C was from L2 to L2 and the problem, I remind you that the setting of the task was only this, because we have no instrument just now to calculate. Later we obtain the instruments to calculate the norm. I don't want to write the square roots, so I calculate the norm in square for shortness. So it is AB k xt ft dt absolute value square dx. Again, first step is standard step. First step is standard step. Put the absolute values inside the integral. So it is AB integral, the here square, but in the brackets, and dx. You need to do something with this integral to obtain the norm of function f. So you must obtain the integral of the square of function f. The standard way is what? Cauchy-Bonnikovsky, yeah. To this integral, we apply the Cauchy-Bonnikovsky inequality. Apply here. So it is yes? There are no square roots because here squares. But it is the constant. And then we have integration of variable t and variable x of the square of function k on two variables. So it is just the norm of function k in L2 of two variables multiplied on the norm squares of the norm of function f in this space, what we need. So what you can say about estimations of the norm?
Take the maximum in x.
No, not the y maximum.
Okay.
They're not a maximum. So by Cauchy-Bonnikovsky, we just obtain the integrals. This is just the norm of function f squares. So the norm of operator as usual, it is less. Do we have an addition problem for an operator of this operator? Do we have this problem? Let's apply this. We can apply item C when consider this operator in space of L2. But in C01 it is simple. A yes, maximum of x by definition of space C01. And if we write one space, then we assume that operator walks from this space to this space. Yes? When we write one space. Again, first estimation. This is less than norm f, again in space of continuous function. So we obtain that it is, then you change x on 1 and the length of the interval is 1. So we obtain this estimation. And if you take function f equals to 1, identical, then af equals to x and maximum af equals to 1 on interval 0, 1. Yep. So in the space of continuous function, it is easy to obtain the result. And what changes if we go to the space L2? We change the norm. First step, it is convenient to change this operator on operator with the fixed limits. We just consider with operator with fixed limits. what we can say about function k? Compare these two integrals. Kxt equals to 1 if t less than x. T less than x is here. And here is 0. Such operators is named, it's particular case of operators with triangle kernel. It's easy to understand why it is triangle kernel. It is on triangle 0, and on another triangle maybe not be constant, maybe some function. Maybe some function, moreover. But if you take these functions, but we can't take it because the assumption to item C was that it is not continuous. It is not continuous, but it is from L2. This function, of course, in L2. So this transform is clear, yeah? Not? I, without any thinking, change the interval 0x to 0, 1. But they must be equal. Yes. I hear that this is 1. So my function kxt must be as following. It must be 0 when t greater than x. Because we have no integration with t from x to 1. So from if t greater than x, function must be 0. Here t greater than x. Here t equals x. Here t greater than x. Here t less than x. Yes?
Perfect. Okay, yes.
So understand? Here 1, and then you just multiplication 1. If you want to solve some function k, so you obtain here some function k. Okay, it's so-called examples of Volterra operators. We discuss Volterra operators when we start with Fredholm theory. And you directly use the results of item C. We know that the norm of operator less than the norm of function k in L2 of two variables, 0, 1, just in this. It is not just the square of this triangle. Function equals 1 to the triangle. So it is just the measure of this triangle. It is 1 over 2, 1/2, and the square root. And some spoiler, the norm is less. And spoiler, that the norm of this operator, when we start with Hilbert-Schmidt theorem, it's just a program, we show that the norm of this operator equals just this number. And of course, t over pi is less than this number. It is above 0.7. And this is less than 0.66666. It is less than 2 over 3. So it's all with homework. So theorem CAB star is isometrically isomorphic to space BV0 AB, which consists of all functions of bounded variations with the normalization and try to remind me to discuss why only for interior points. For point A, it is easy to explain. Point A have no left neighbor. So in point A, you can't consider continuous from the left. But why it is impossible sometimes to do it in point B? So then for any functions from here, we can find function, unique function from BV, such that our functional acts as a Riemann-Stieltjes integral. Just a Riemann-Stieltjes integral, and the norm G equals to norm G in BV 0. But one remark. If you see in space LP small, LP capital, these theorems on isomorphism are very convenient, and they are simplified calculation of the norms. But for this space, it is more easiest to by definition. Why? Because this norm is supremum. Supremum of action of a functional on the unit sphere, for example. And this is a full variation of function. A full variation is supremum too. But when the norm is integral, the humanity have a lot of apparatus to calculate integrals, for example. And maybe more small apparatus, but large apparatus to calculate sums. But supremum is more difficult operations. So you change one supremum and another supremum. So let's prove. First, just two steps. First steps of this direction. Let G from BV0, AB construct GF just as theorem says. The integral of Riemann-Stieltjes. And try to find the estimates. It is just less than norm F. Yes. Then you obtain that it is and this is just gives us a full variation. Because by definition of the Riemann-Stieltjes, it is the limit all over subdivisions of these sums. So I think you understand that this integral of modulus of differential is the limits of these sums. It just gives us just full variables. Moreover, we obtain limit when we take the subdivision on the smallest intervals. And we take the smallest intervals, we immediately obtain the variation as a limit of supremum. So from these estimations, you obtain that the norm of yes. On this step, I don't want to show the equality. We obtain the equality on the first, on the second. So just it is sufficient to understand that any function of bounded variation generates a functional as Riemann-Stieltjes integral with the estimation of the norm. But on the second step, we obtain the inverse inequality. Second step, when we take the continuous functional, and then we construct the function of bounded variation, which represents this functional as an integral. Okay. So second step. So I remind you, we show that this is equality, but we show that it's on the second step. We show it on the second step. So second step, let is from this. And we use Hahn-Banach theorem. We use it. So it is an example of the application of Hahn-Banach theorem. What? We know that CAB is a part of this space, L infinity. And the norm are the same. Here the essential supremum, but essential supremum for continuous function coincides with simple supremum, maximum, moreover maximum. Do I need to discuss what the norm in this space? What is essential supremum? The norm in L infinity? It is so-called almost bounded functions. Almost, yes. It may be unbounded, but on the sets of measure 0. So you take supremum not only all interval AB, but without subset E, for example. And then you take infimum all over measurable sets of measure equals to 0. But continuous function are bounded function. So essential supremum for continuous functions, just a maximum, usual maximum. So this is embedding with the preserving of norm. Then, by Hahn-Banach theorem, you can extend this functional extension by Hahn-Banach theorem. By Hahn-Banach theorem. Why this construction is useful? Because we can now apply our functional on the discontinuous function. In L infinity, function can be not continuous. So we can apply G tilde, G capital tilde, on not continuous functions. This is an indicator or characteristic function of subinterval AT. So if you want, you can write the indicator, but I usually use characteristic functions of x equals to 1 fx less and 0 x less than t on interval AB. This is not continuous function, but we can apply G tilde. It is in L infinity. This lies in L infinity. The application of functional on any element from the linear space is a number. But this is a parametric set of functions. It depends on parameter t. Functions depends on argument x, but this is not one function, it is a family of functions. So here we obtain the numbers dependent on t. This is function of t. Define this function of g of t. And I claim that this function g is the function we need. We show that this function is of bounded variation, and we show that our functional g tilde is integral, is a Riemann-Stieltjes integral. Okay. What we can say about some remark on if I take a characteristic function of subinterval inside AB, how we can write it? T1, T2, B, A. It's easy to see that you can write it as following. And your functional is linear. So it is okay, yeah? And now take some division. some subdivision of interval. And by this subdivision, construct function f sub t of x. It equals when k less than n and equals signum it's just because the last interval must be closed. Here semi-intervals, and last intervals I need to take the closed interval. So we can write this function in the following way. It is signums g tk minus g tk minus 1 on characteristic function of semi-interval. And for the last, this is closed. I don't write the except the last sum item. But you must understand that for the last item, you take the closed bracket. And your functional g tilde is a linear function. So this is a number. This signs, it is a number. It takes away out of the action of functional, yes? And then you act by functional on each this characteristic function. And we know that on each characteristic function, just the difference. So we obtain the difference on functions, multiplied on signum. So we obtain that it is equal to this sum. And what we know about the normal function, ft in L infinity. It is signums. The absolute value of signum is 1 or 0. So the norm, if function g is not 0, so it is less or equal to 1. Yes? We know the definition of the norm on the sphere, on the ball. So the norm of functional g is not less than the action on the function of ft. Because it is supremum of all sphere, it's just some elements on sphere. This is in L infinity. So, and this we obtain that it is a variation of function g on subdivision t. And we can do it, we obtain this subdivision t. So we can do it here tilde for any subdivision t. This is not depends on subdivisions. Can we take the supremum all over subdivisions? Take sub over subdivisions. Here we change nothing. It is normal functional g tilde. And here we obtain that it is the full variation of function g. What we obtain? What we obtain? We obtain that this function is of bounded variations. And moreover, by Hahn-Banach theorem, it equals to the normal function g. So we obtain the inverse inequality. We obtain the inverse estimations. Then, by definition of function g, is it obvious that from definition we obtained immediately that it is 0 at a? Because subinterval from a to a is a 0 subinterval. Linear functional 0 elements gives us a 0. So function a in 0 is 0. Additionally, it bounded to variations. So it is difference of two functions which are increasing, not non-decreasing, not strictly increasing, but increasing. Any increasing function has finite or countable sets of points of discontinuity of first type. At these points, we take it continuous from the left. And this does change the integral Riemann-Stieltjes for continuous functions. And what we need to obtain additionally, what we not show in step 2. I take functional from CAB star. By Hahn-Banach theorem, I extended it to this is to L infinity star. To this functional, I construct function G small and show that this function from space of functions of bounded variations. But what we not show?
Uniqueness.
Uniqueness we obtain if we make it continuous to the left. But we don't show that this functional is integral. Is we show it? We don't show. We construct only function g, some function g of bounded variations. And we have no connections between functional g capital and integral of Riemann-Stieltjes type with the function g small. But it is not a difficult problem because this is maybe some reminders of the definition of function f, yes? What we know that g of ft here, yes? ft we have here. And let's consider this integral. We know that this is variation of t of function g, yes? Here we calculate it. Here we calculate. And now calculate this. Now calculate here, this. It is sum of integrals from tk minus 1, tk, signum g tk minus gtk minus 1, multiplicated on dg, on differential. This is number, we can take it out of the integral, yes? Signum is just a number. So we can write the sum signum gtk minus gtk minus 1 integrated on dg tk minus 1 tk. And what gives us integration of differential? Newton-Leibniz formula. Difference of g of up limit minus low limit. So this integral, this last integral equals to g tk minus gtk minus 1 multiplied on signum, and we obtain the sum of absolute value of oscillation. So it is just variation of function g over subdivision t. So this result and these results are the same. So we see that the function of for ft, we have integral. We show that they are coincide. So function is linear function, yes? And integral preserves linear combinations. The integral of linear combinations is linear combinations of integrals. So if I change the one function of this type on the linear combination of function of this type, ck, f, some different subdivisions. We show that for any function of subdivision, it is an integral. So it is equals to this. This is equals for this. ftk dg, and this is equals to this integral of sum ck ftk dg. Is it clear? For any linear combinations of functions of such type. And the last, can we approximate any continuous functions with step functions? You understand that functions f sub t is a step function. It's on some intervals is a signum. Then you multiply it on some constant ck, take linear combinations. Again, some step functions. So can we approximate any continuous function by step function? What you can say about this object? Can you write the graphics of this? For example, for positive. X is a variable, independent variable. If x from 0, 1, n, what you can say? Oh, but sorry, that. X multiplied on n is smallest than n, smallest than 1. The integer part is 0. So it is, and here our x. What you, from here, from 1n to 2n. What is the integer part for this 1? And you divide it on n. Understand? So for any f continuous, define this function. Because the argument is a stepwise function. This is a stepwise function. So it is functions of this type. This function of this type. This function type sum ck f tk. And it is converged to f pointwise, yes? You see this? Because the argument converged to the x. This is converged to the x. So these pointwise functions converge to the f. And then what you can say? Our function is bounded, so it is continuous. So it converges to the value of function on f, because fn converges to f pointwise in L infinity. And this is converged by, for example, Lebesgue theorem. We can take limit inside the integral. It's converged to the f dg. So we obtain the equality of the integrals to the action of functional to any continuous function, for any continuous function. For some function for L infinity, it can act in another way, maybe not integral. But for continuous function, by this construction, we show that the function is a limit, is an integral, is an integral. Let's consider the homework problem and try to calculate the norm with this theorem, and you see that it is not convenient instrument. So remind me what the functional was. The space was C minus 1, 1, and functional was plus was, yes?
Yes.
Plus 2f in 1, 2, e minus f 1 over 4. Try to write this integral, this function in this way. Try to then you first step. If you want to calculate the norm of functional with the help with this theorem, you must first write the functional in the integral type, and then calculate the variation of this function. First, I remind you that first, any functional, the value of function in point with some coefficient alpha is just integral with the step function g. Step just in the point t0 and the high of this step equals just to this coefficient alpha. Is by definition of integral. Left to this point is 0, all differentiables. Right to the point of t0, all difference are 0. And only when we make a step from left subdivision point to the right subdivision point, we obtain the step, the jump with the high alpha. So here we have x. Oh my God. It is minus 0, 1 minus x dx. Yes, then we must divide by definition the absolute value in two sides, in two parts. So it is so you can try to begin to draw a picture. So this is inside the differentiable. Yes, it is part of the function g. Minus x squared over 2 is just such function. Yes. To the right, it is x squared over 2. It is only integration part. And then use these parts. In this point, you make the step hour, so the next picture will be it is 1 over minus and square 1 over 4 and up at 1 minus half of 8. So here here was from minus over 2, yes, here. Yes. Then 1 over 4 and step. It is only a picture of function g, and now calculate its variation. Is it convenient? Not. I think the step by the calculations by definition is more. Okay, let's write some homework first. We have a normed space. X0 is closed subspace, non-trivial. The main idea that you can construct a functional which is non-zero functional, but it is zero on non-trivial subspace. For any non-trivial subspace, there exists non-zero functional, which is zero on this subspace. But I give this problem with some additional information on this functional. Let x is not from x0, and then you can define the distance between x and x0. By definition, it is infimum of this norm all over x0 from our subspace. And because I take closed space and element is not from this space, then it is positive number d. Positive number d. Then exists functional f and x such that norm of function f equals to 1 and f of x equals just to d. And domain non-zero on subspace 0. And this is only additional normalization. It is additional normalization of functional. The main idea of this problem that for any closed subspace there exists not functional which is not zero in whole space, and on this subspace is 0. Spoiler repeat with some modification first step of proof of theorem Hahn-Banach when we construct extension on one element. With some modification, you must construct continuation on this element you given, and see what you can do with this. Second, if
Sorry, the question. This functional gives the distance for only one particular point.
yes, we given 1 point. This additional normalization for this element, it is this step is a hint how to construct. It is just give us a simplification of the solution. If we take away, it is not. It is something more complex problem. This is just a hint how to construct it. If you know the way of proof of Hahn-Banach theorem. Second, if X dual is separable, too. Hint, use task 1. I like to solve problems by chain, step by step. Immediately from this problem, you obtain that L infinity star is not L1. Immediately, because this is separable, and L infinity is not separable. And inverse, the dual for L for separable can be not separable. L1 star is L infinity. It is separable, and this is inseparable. So the application only this way. The separability of dual guarantees separability of origin space. Third, it's not from functional analysis problem, it's from theory of functions. For what parameter alpha, it is bounded variation on 0, 1. Just to pick what means bounded variations, because you must understand that functions have large oscillation near 0. Yeah, but if you, I don't spoil. 4, and the last, it is some task for and examples of use of functionals. let's m equals such function from C0, 1, for which the integral, for example, equals to 0. Find the distance we know the way how to find the distance in Hilbert space by orthogonal complement at its norm. Space C0 of continuous function is not Hilbert space, so it is not orthogonality, but the definitions of distance exist in any norm space. But how you can solve it? I change the order, the logical order of tasks, because in these formulations it is difficult. But do you understand that the set M described as a kernel of the functional, of linear functional? It's equals to 0, it's just a linear function. And 5. For example, to prove that it is closed by definition is not it is not difficult, but it is not simple. But for any continuous functional, the kernel, of course, is a closed linear subspace, automatically. And the distance for any element to the kernel, to the kernel, equals to the value of this function, of this element, divided on the norm function, and here not. But in this way, this is a simple problem. This may be not simple, but this is simple. To calculate the meaning of functional, it is not difficult way, and to calculate the normal function. And you have very simple analogies from the school geometry. School geometry, you have line ax plus by plus c equals to 0. And you have point x0. What is the distance between x0 and line L? School mathematics. It is ax0 plus by a0 plus c divided. Compare this formula with this abstract formula in any norm space. It is not linear functional because we have c, but it is linear function. It's a linear function. So this is just simple analysis for this. So I think it's sufficient. 5.